We've all been there. You're trying to get work done, but the application stalls out, leaving you staring at a spinning wheel. So you submit an IT ticket with a vague complaint. The network is slow. Looking at these rows of physical server racks, you're seeing how networks used to be built. They were physically centralized, with the hardware entirely owned by the company and contained safely inside a single building. In this simple floor plan, troubleshooting was straightforward. You sent a ping to a local server, and if it lit up green, you were good. But that closed loop is gone. Work went remote, devices multiplied, and applications moved to third-party cloud servers. A simple ping test can't tell you why a video call is lagging if the data is traveling through 3 different internet service providers. You can't pull hardware you don't own. Because enterprises no longer control the infrastructure their data travels on, engineers have to rebuild visibility piece by piece. They use layered telemetry to locate invisible points of failure across systems scattered around the globe. The investigation always starts at home. Before looking outward, engineers have to rule out their own hardware. They do this using SNMP, or Simple Network Management Protocol. It's a method for polling local routers and switches to pull their core functional metrics. Looking at this diagram, we see the router's data separated into CPU and memory loads. Because these bars are sitting safely in the green thresholds, we know the hardware isn't physically failing or overloaded, but the user's application is still stalling. Since local equipment is healthy, the bottleneck is in the data moving through it, not the physical box. If the pipes are intact, the next step is observing the water. We need to see exactly what the traffic is doing. To map that traffic behavior, engineers rely on NetFlow. This protocol captures metadata about every data packet crossing the router, recording its source, destination, and total volume. This area chart illustrates why that visibility matters. The baseline shows normal, uniform data traffic, but then a massive vertical spike suddenly consumes all available bandwidth. NetFlow tells us that spike is an unauthorized mass data backup. In our current investigation, however, the flow data shows normal volumes. The traffic is successfully leaving the building without causing congestion locally. It's getting lost somewhere outside. Once those data packets cross the enterprise firewall, physical control ends. Tracking them across the public internet requires a different method of measurement. The data is now navigating the public internet and third-party data centers, a space where enterprise visibility typically drops to 0. To see into that blind spot, engineers deploy synthetic monitoring. They generate simulated user traffic, sending automated probes out into the network. In this topology map, we can track that digital probe hop by hop. It launches from the local node, travels across public internet service providers, and then turns red right as it hits a specific third-party server. This process isolates the exact failure domain. It proves whether the delay is happening inside a lagging software provider or at a misconfigured ISP link along the route. By tracing the exact path the data takes, engineers regain insight over networks they don't own, giving them the evidence they need to hold third-party providers accountable for the slowdown. Looking at this engineer in the server room, we see the final step. To resolve the incident, they must centralize these disparate data streams, the device health, the flow volume, and the synthetic paths, into a single analytic environment. Syslog event correlation adds a layer of operational context. This protocol records system events and configuration updates, allowing the engineer to see if a firewall rule was modified at the exact moment the latency started. This Venn diagram represents a modern, AI-assisted dashboard. As the data streams from SNMP, NetFlow, and synthetic tracing overlap, they instantly cross-reference each other to illuminate the single central root cause. For our frustrated user, the dashboard confirms the source of the lag. The slowdown was caused by a specific misrouted cloud policy executed hundreds of miles away, completely independent of their local hardware. This is the evolution from traditional network monitoring, which simply waited for local machines to break, to network observability, the practice of understanding exactly why highly complex distributed systems behave the way they do. The illusion of a seamless, perfectly connected digital world requires constant, triangulated telemetry. It's the only way to predict and isolate invisible failures before a user ever has to submit a ticket.